Okay, we're going to be recording this part of the session. If anybody has any objections with the recording, then please say so now. Okay, thank you. So what we're going to be doing now is that we're going to be doing some exercises, exercises that have to do with arrays of capacitors in series and in parallel. And so, as we mentioned, it isn't necessarily going to always be the case that we're always going to have a series array and always going to have a completely parallel or completely series array. There's going to be combinations of these. And in the end, what we want is to find the total capacitance of the array. And in some cases, we're also going to want to see of the individual elements of the array or the circuit, how the charges and the voltages are distributed. So we're going to look at these 4 examples. In each of these examples, we've got capacitors, and these capacitors are connected amongst themselves in some sort of combinations of series and parallel. So what I'm going to do now is I'm going to walk through how we approach these problems. I'm not going to do the numerical calculation. I'm not going to do the calculations. We're gonna leave that for next session. I'm just going to walk through how we would approach these circuits. So first off, think of these circuits kind of like a puzzle, okay? And kind of like these puzzles where you have to unravel things. So you kind of have to unravel things, and once you unravel them, you have a complete thread or solution. That's kind of the way we're going to be doing it, or kind of like when you're working with a Rubik's Cube and you start placing things until you have a complete cube with all of the faces complete. That's kind of the way we're going to be approaching each of these circuits. So we're going to be raveling and unraveling. So let's look at the first one. How many capacitors do I have there in that circuit, in this first circuit that we have here? And we're talking about this one here first off. This is the base circuit. How many capacitors? We've got 3, right? And the first thing we've done here is that we've named them. I'm going to call this one C1, this one C2, and this one C3. Okay? And we need to start identifying the types of connections we have. And once we start to identify them, try to reduce the components until we have only one component. And so in this capacitor, and what we're going to be trying to do is that we're going to be trying to look for groupings of capacitors in either 2, maybe 3, that we can clearly identify if they're in series or in parallel, and try to work on that. So in this first circuit that we have here, we've got 2 capacitors here. We're going to look at these 2, C1 and C2. Can somebody tell me what type of connection do those 2 capacitors have? Is it a series? It's series. It's a series connection. So we've talked about equivalent or total capacitance. So these 2 capacitors are connected in series. And so I can combine those 2. I can combine those 2 into one capacitance that's equivalent. I'm going to do that, and I'm going to call that equivalent capacitor, I'm going to call it C12. Okay? And I can do those calculations. We just did it previously. I'm not going to do them right now. I'm just kind of walking through how we would approach them. C12 would be the equivalent capacitor of C1 and C2 that are connected in series. Okay? Are we okay up to that point? So we grabbed those 2, we made them 1. And I'm going
by adding them.
Well, JC, right now let's not worry about the operations. Remember that if it's correct well, these are in series. So remember that in series we don't add them. In series it's the reciprocal. okay? In parallel is when we add them, okay? So in this case,
okay, thank you.
in this case, the reciprocal of C12 would be equal to 1 divided by the reciprocal of C1 plus 1 divided by the reciprocal of C2, because they're in series. Okay? Okay. Questions up to this point? What we've only done is to reduce. Instead of having 3 capacitors, now I've got 2. So I'm making the circuit smaller, okay? Because I want the total equivalent capacitance. So questions up to this point?
No.
And we would do the calculations. And I'm not going to do the calculations right now, but we would have to do the calculations. Now we've got this new circuit with C12 and this capacitor over here, which is C3. Let me actually write that down there. It wasn't copied. Give me a moment. This is C3. Okay. Now we've got those 2 capacitors there. Okay. And let me just put this where it should be. There we go. That's better. Okay. So we've got the 2 capacitors here. Now the equivalent capacitor of these two, C12 and C3. And can somebody tell me what type of connection do we have here between these 2 capacitors?
Parallel.
This is parallel, correct, JC? And so this connection is parallel. It's a parallel connection. And we just said that a parallel connection is the sum of the capacitors. So this parallel connection, which is also actually going to be this equivalent capacitance, C total, is going to be equal to the sum of those 2 capacitances, which is C12 plus C3. And this is how we would find the total capacitance, okay? We kind of analyze the circuit and we're going to try to reduce it until we only have 1 capacitance. And how are we going to be doing that? We're going to be identifying the series and the parallel connections, okay? Questions here with this one? I'm not going to do the calculations. I'm going to ask you guys to do that on Friday. Questions here?
Negative.
Okay. Okay. Now let's go. Let's look at the next one. Okay. So for the next one, it's a different array here. Now we've got another circuit here. This is the circuit we're looking at. This one here. And we want to find the total capacitance for this circuit, okay? And so can somebody tell me what type of connection we have here with these 2? We've also numbered them, C1, C2, C3. Can somebody tell me what type of connection we have there?
Then you said it was parallel?
It's parallel connection, correct. Just also, give me a moment here. Just want to verify that all of the values are copied. Yep. There we go. Okay. It's a parallel connection, correct. So this is a parallel connection. Spooky writing. This is a parallel connection. And so a parallel connection, we know that it's the sum of the capacitances. So this parallel connection, we're going to call it C12. And so C12 is going to be equal to C1 plus C2. And that's going to give us this capacitance here. So we reduce the circuit by one capacitor. And we're starting to compact the circuit, okay? Now, the new circuit that we've got over here, okay? This circuit that we've got here, what type of connection do we have with these two capacitors?
Series.
It's series, correct. So now these two are going to be in series. So these are going to be in series. And so if they're in series, it's the reciprocal. So this series connection is actually going to be the total capacitance that we're looking for. And so 1 divided by C total is going to be equal to 1 divided by C12 plus 1 divided by C3. And that's going to be that's going to be, with that, we can calculate the total capacitance for that one, okay? And so again, what did we do? We kind of identified the connections and kind of went through that, okay? And walked through each of these, okay? Questions with this one before we start to add a bit more complexity?
Negative.
Okay, good. Okay. Now let's look at this one. And this one is a bit, now we're adding a bit more complexity. We're looking at this circuit here. And this one's a bit larger, okay? Oh, I forgot to mention something that's actually kind of important. When we're talking about equivalent capacitance or total capacitance, it always has to be between 2 points. And depending on where those points are located is how we're going to be doing the analysis. So there's always going to be 2 points that are going to be open in the circuit, and that's where we want to find the equivalent capacitance, or we're measuring it. So that's going to define how we're going to start working. So how can we approach the reduction of this circuit? Well, the same. We're going to try to identify connections that are purely parallel or purely in series. So for example, this is interesting. Can somebody tell me these two capacitors, are they connected in series or in parallel?
I think it's series. No.
Neither, no?
It's yeah, let's do it. Let's do a voting. How many of you think it's series? Some of you do. How many of you think it's parallel? Some of you do. How many of you think it's neither?
Me.
Maybe both.
Well, actually, the thing we have to remember is that we have to, if it's going to be in series or in parallel, we have to clearly identify a series or a parallel connection. There can't be any ambiguity. This connection here is neither series or parallel because both of in a series connection, kind of think about it this way. Remember that all of the components have 2 terminals, okay? In a series connection, we've got only 1 point of the terminal connected between the 2 elements. and that terminal isn't connected to anything else. So if we look at any of the two terminals here in the circuit, any of the two terminals is connected to the other capacitor, but it's connected to something else. Okay. Let me because this is important, because this can generate a lot of confusion. So give me a moment. So the answer is it's neither. It's neither series or parallel. So in a series, let's use the Justice League to see if the Justice League. So in a series connection, remember that each of the elements has two terminals. Batman has two arms. Superman has two arms. Both of them have two arms. Okay. In a series connection, one of the arms is connected between them, and there's nothing else connected there. Okay. Doesn't mean we can't have things on the other sides, but in this connection between those two arms, there's nothing else connected there. Okay. So what could generate something like kind of like the one we're looking at there? Well, let's assume that now Shazam arrives and Shazam tries to join there. This was a series connection because there was only one thing connecting the both of them. Thinking about the flow of energy, of electrical current or fluids or whatever you want, the flow isn't interrupted from one point to the other. But then Shazam arrives and tries to grow, because Shazam is never invited to anything. And so now there's something connected here between those two. The flow is interrupted because now part of it goes through Shazam. So this is not a series connection. Okay. So that's kind of like a tip. Okay, well then, is it a parallel connection? Well, for a parallel connection, both terminals have to be connected together. Okay, have to be connected together. Each of the arms of the other has to be connected to the arm of the other one. Okay, and so here also we've got this arm connected to something else and this arm connected to something else. So it's neither a series nor a parallel connection. So if it's not clearly a series or a parallel connection, we can't do a reduction of those components. So let's see if we can identify, let's say, a purely series or purely parallel connection in this circuit. So if we look at C1 and C2, which are these two here, we see that this is a parallel connection because we've got the two terminals of this one connected to the two terminals of this one. It doesn't matter that this one is connected to something else, as long as the two terminals of one element are connected directly to the other two terminals of the other. That's a purely parallel connection. And I think you noticed that I'm using, please remember that my arm hurts. So I think, and this is being recorded, so I believe you understood that I'm using purple for parallel and orange for series, okay? So I don't have to write down parallel again. Please don't make me write down parallel again. And so the purple is a parallel connection that's going to give us this capacitor here, which is C, which we're going to call C1, 2. This connection is reduced there. Okay. Now we've reduced the circuit to 2. Now we can look at the new circuit and we see that these three capacitors, this one, and this one, there's a series connection here because the terminals are connected amongst themselves and there's nothing separating. In this case, imagining that we had a flow there. So these three capacitors would be connected in series. And remember that the orange is the series. And this gives us an equivalent capacitor. Obviously, we would do the calculations. Next up, we've got these two capacitors that it's the same as the first situation. These two are going to be connected in parallel. And that gives us an equivalent capacitor here. And lastly, we're going to have these three that are, again, creating a continuous circuit that isn't broken. And so the connection between these three is series. And the series connection is going to give us the total capacitance. Okay. And again, we're going to be doing the calculations next class. But it's important to understand kind of the procedure or the flow we're kind of trying to do to identify the different components. Okay. Questions with this one before we move on to the next one. I'm going to go through it again. We looked at these two. These are connected in parallel. We reduce these two and we call it C12. Then we've got these three connected in series, C12, C3, and C4. We reduce these three and get this one, C1, 2, 3, 4. Omar, please go ahead.
Yes, my question is is this the only way to approach these problems, or can there be like multiple paths?
Oh, depending on the problem, there could be multiple ways of doing it, because you might be able to find some sort of these examples at least these three examples, Omar. It's basically one approach because of how they're structured, but there could be a more complex array where you could start doing the reductions at the same time. So you might identify two connections that are in parallel that you could reduce, and then you could do a couple of others in series. So there might be more than one way to approach it, okay? The important thing is to clearly identify what elements are connected in series or in parallel, okay? But yes, there might be more than one way to approach it. In this case, this would probably be the only one, because we can't start off doing any reductions before we do this one here. However, for example, what I did here is that I identified three components in series here. Another way to approach this, Omar, is to always work in pairs. So I'm going to reduce these two first, and then the result, I'm going to do it with this one and start doing it in pairs. I'm grouping I'm doing it in groups of three in some occasions because it's clearly identified there. But there could be different approaches. Okay, any additional questions with this one? Yes, daughter.
Es que encontraron una entrada de algo que mantiene una carta.
Ah, qué bien, ok. Ahorita me lo enseñas porque estoy ocupadito en clase, ¿ok?
¿Quieres que la abramos?
La abrimos ahorita en un ratito, ¿ok? Shit. Oh, I thought I'd muted. I didn't mute. Okay, so
La voy a abrir.
so let's go on to the next one. This one is looks more daunting. Oh, this is a good example of what Omar was asking. So this one could actually, Omar, this one could actually be approached from more than one side, actually. And I'm going to explain that in a moment. So for this circuit, we also have to try to identify series and parallel connections. I'm going to do the walkthrough with this one that I have here, and then I'm going to talk about a variant that we could do that could also could take us to the same result. So here, we're going to identify that these two are in series, and we'll reduce that one to C12. Then we can identify that these two are in parallel, and we could reduce it to C123. then we can identify that these two here are connected in series. And it gives us C1, 2, 3, 4. And even if I have this cable up to here, this is actually equivalent to having the connection directly here. And so these three are connected in parallel. And that would take me to the total resistance. Okay? That's one way in which we could approach it. Can somebody identify another way which we could have started off the analysis that that is actually going to take us to the same result, but it's a different approach? Instead of starting off with those there, anybody?
I thought that at the beginning we could start at the right side, the small square.
Yep.
It could be a parallel.
Correct. That's exactly correct, JC. So I'm gonna do it in a different color. I'm gonna use a darker color for the same. I'm gonna use the pink here. Pink is gonna be equivalent to parallel. So I'm actually I'm gonna do this. Let me save this. Another approach could have been to say that these two are connected in parallel. And then they would be connected in series with this one, which would be connected in parallel to this one. And they would all be in parallel with that series connection, which is just kind of a mess here. I'm actually going to add to the PowerPoint, I'm going to add that version of the solution, which could also
Professor?
be valid. Yes, go ahead, Jason.
At the end of this step, when you had a parallel with all the three C's,
Mhm.
like, and so you add all three C's and they'll give you the C total.
Yep, correct.
Okay.
Correct. And so what JC was mentioning, that we could approach it using starting off here with these two in parallel. That's correct. That's kind of an example of what Omar was asking, if these could have different approaches. So yeah, we could approach it from different sides and we should get exactly the same result. Okay. So this section has been recorded. I'm going to upload it to Blackboard in a few moments. And I'm going to ask you guys on Friday, we're going to do some exercises. And I want to. Diles hola, diles hola. No, diles hola.
Hola.
Te quieren saludar.
Hola.
Hola.
A ver,
Hola.
she's doing some. I was actually in a meeting. Trae a tu siso. Trae el siso. I was actually in a meeting that I was coordinating. It was a workshop I was coordinating with some. Oh, I don't have to record this. This doesn't. I'm going to pause the recording because so you have the examples there, and we're